Okay, this is example 13.7, and I want to do both shear and moment diagrams for this. And it's a distributed load. Okay. Across the entire thing. And it's simply supported because there is a rolling joint on one end and a hinge joint on the other. And then there's a distributed load across the entire thing. 3 kip per foot. What's a kip? Kip is 1,000 pounds. And of course we're talking pound force. Okay, so my reaction, okay, so this is 8 feet across in span. So my reaction is going to be symmetric. So I'm not going to do sum of moments. I'm going to say the reaction at A is the same as the reaction at B. So I need 2 reactions to total, sorry, sum of force in the Y. 0. 2 reactions to total negative 3 kep feet spanning 8 feet. Okay. 24 divided by 2. 12. Kips. Okay. So 12 up, 12 up. If I wanted this as a point, it would be 24 down. Halfway across would be 4. And then also I might want it as a distributed load as well. I probably will just keep it as a distributed load and do my shear from that. Okay, so I'm going to redraw my loading because I need more page. 12 and 12, 1,000 pounds. Okay. 3,000 per foot, 8 feet across. Cool. Let's do the shear then. Oh man. Okay, now I could do my shear from here. Okay. So as I travel along my feet, it starts at 0. There's a sudden 12 positive. Let's put that here. So my shear inside of the beam is 12. Then as I move left, there is a negative 3 per foot. So let's say I travel 1 foot, it will be 12 minus 3, 9. Travel 1 foot more, 6, 3, 0. So at 0, I've traveled 4 feet. So 4 times 3, 12. Okay. And now as I keep traveling, I have this distributed load pushing down, 3 per foot. So I travel 1 foot over, negative 3, negative 6, negative 9, negative 12. And at this point, I have a 12 pushing back up to 0. So as I travel outside of the beam, 0. And that's a good sanity check, right? And okay, and this is at 4 feet. And so I know inside the beam, I know the shear force it's experiencing at any point. The maximum shear force it's experiencing is both right before this support and right before this support. After the support, it's 0. So if this were to fail in shear, it would be right where it's being simply supported. Okay. Now we want to do moment. And moment is going to be the area. Okay, so also at the supports, again, they're simply supported. These are hinges. They do not carry moment. So that it's going to be 0 and 0 again at the supports. And it would be awkward to come up with this area, but you could. So I could find the moment at a point just graphically here. I could say we've got a rectangle that's 9 high and a triangle that's 3 high, and this is, let's say, 1 foot over, right? Because I've characterized that from here. I would travel 1 foot, I got down to 9. So I could come up with this area and plot that point. Okay, let's do it. So I've got a 9 kip foot here, and then I've got 1.5 kip foot here. Okay, so that puts me at 10.5. I don't know how to scale it. And then you could do the same. Got a rectangle like this. Another one sitting on top of it. And so this one was 6 and 6. At 2. So now we've got 12 kip foots. 6 kip foot. So from 1 foot, it went from 10.5 to the next foot, it went to 18. Okay. So my scale's a little off here because I got another foot I could go. I'm going to go to the point here though. So where it crosses 0, that's the local maximum. That local maximum is going to be this triangle. That is 12 high and 4 long, wide. Okay, so that's just base times height times a half. That's the area of a triangle. So that's 48 kip foot. Nope, times a half. 24. So I'm up here at 24 at 4 feet. And then I also found 10.5 at some point. And, well, at 1 feet. And then I also found 18 at 2 feet. And then 24. So from experience, I can tell you that if the shear diagram is a line, then the moment diagram is a parabola. Okay, and it's symmetric here in this case. So over here there's also 10.5 and 18. And it peaks at 24. kip feet. Okay, so taking these little areas is a lot like doing the cut of the beam.